right, let's take a peek at number 15 at the bottom of the front page there. I want you to find the probability that a dart thrown at this target, based off of whatever they're asking for. And in number 15, it wants us to find the probability that a dart would land in the center A. So very similar to the problem we did yesterday. We have a dartboard. It looks like a dartboard. What do you have to find if you're figuring out the probability of it landing in the center, which is the bullseye? Mackenzie? Yeah, so we need the area of the whole dartboard. So we have to find the area of the square. And Mackenzie, that would be? Yeah, because you're taking 24 squared, which is 576. The reason we need that number is because that's the total that would go in the bottom. So the total area has to go in the bottom, which is the whole dartboard. And then Mackenzie, what else do you have to find? Yeah. And the area of A would be pi. And then each one of those little rings has a radius of 2 inches. So each ring has the same radius of 2 inches, so that would be pi r squared, which is pi times 4. And Mackenzie, what is approximately pi times 4? 12.57. So then to find the probability, you're taking the 12.57 and dividing that by 576. So the probability of getting this center, which is the bullseye, would be what you're looking for, the little space of A, over the total space of the whole dartboard. And if you flip your sheet over, it should have given you a value. Mackenzie, what was that value? 0.22. So approximately 0.22. Just talking about number 16. Number 16 wants you to find the border F, which is outside here. So again, very similar to what we did yesterday. So if I want to find that area, you first have to find the big circle and subtract the area of the big circle from the area of the whole square. And then that gives you the area of the shaded region. So find the area of the big circle, subtract it from the area of the square, and then that would be the value that you would be using. Are there other questions on the homework that you wanted to go over? So we're going to continue to talk about probability today, but we're going to talk about probability of compound events, which means we've got 2 events that we're trying to combine together. So still using the probability that whatever you're looking for goes on top out of the total, but now we'll try to combine some events together, having an event A or event B happening. And then tomorrow and Friday, we'll look at section 10.5. We'll spend 2 days on 10.5 because there's really 2 different types of probability that are kind of contained in 10.5. So we'll look at something called conditional probability and then something called, it's the multiplication rule, but we'll be looking at multiple events occurring one after the other. So in your packet, if you'll find section 10.4, just a reminder, next Tuesday we're going to have a probability test. So on the concepts of probability, permutations, combinations. And then we are going to start statistics next Wednesday and Thursday prior to our 4-day little spring break. We'll just be talking about like mean, median, mode, range, something called standard deviation. That will be like the new part that we'll be going over next week. So we're just going to briefly start statistics. It should be a really easy 2 sections. So today we're going to find probability of compound events, which is either the union or intersection of 2 events. And there's two different options that we have. So we either have overlapping events or we have what's called disjoint or mutually exclusive events. And I'm going to draw a little Venn diagram so you can kind of see the difference. So overlapping events, I would have two different things occurring. So we'll say A versus B. And while there are some options separate from the two, there are also a couple that they share. So event A shares something in common with event B. So we would consider those to be overlapping events. The other option of compound events would be if they're disjoint or mutually exclusive. So you'll either see the word disjoint or you see the word mutually exclusive. What do you think is happening with those two? If events would be disjoint or mutually exclusive, what do you think that would be? Julian?
Does that mean it can be like either one but not like both?
Right, so it could be either one or the other, but there's not going to be that both occurrence. So my events would be totally separate. So again, here's A, here's B, and we have things happening in A, different things happening in B. So there is no overlapping where they don't share anything in common. They really are separate. So one event is totally separate from the other. We'll look at examples of each so you can kind of see why one would be considered to have a common outcome and the other one would be kind of separate from each other. So there are two little formulas that we're going to use dependent upon if I have two events that are what we'd say that common, where they overlap, they have something in common, or two events that are disjoint or mutually exclusive. So it says if A and B are any two events whatsoever, then the probability of A or B. So that's the word you're going to see in all the questions. What's the probability of this thing happening or this other thing happening? So we would look at finding the probability of A, just like we did yesterday. We're going to add that with the probability of B. So when I want to find the probability of one event or another one happening, I add the two probabilities together. However, there's going to be an overlap, and we have to subtract the overlap. Because there is a part that I counted in A, I recounted that same number in B, so they were like double counted. So we need to subtract the part where they kind of have that piece in common. So that's the overlapping part that we would subtract.
Would you multiply them together?
You know what, we don't have to multiply them because you're already going to be given that number. So it's going to say this is the probability of this happening, this is the probability of that other thing happening, and then we're going to like physically count the number of both. So we would be able to see that number of both. We wouldn't have to multiply it. Other questions? So it's more of like counting how many times do they both occur, not the multiplying part. The other option is when they're disjoint, which means they're separate, they have nothing that overlaps, so we don't have to take into account that they both could occur, and we just have to find the probability of A plus the probability of B. So the probability of the first thing plus the probability of the second. But there's no overlap, so we don't need to worry about subtracting anything because they don't have outcomes in common. So the first problem here says that they are disjoint events, which means they're separate from each other. So it says you roll a 6-sided number cube, or a die. What's the probability of rolling a 2 or a 5? Because a 2 can never be a 5, they're considered separate events because a 2 cannot have an and 5 at the same time. So we would just find the probability of getting a 2, add it with the probability of getting a 5. It can never be both. A 2 cannot be a 5. So Abby, how many 2s are on a 6-sided die? Out of 6. How many 5s are on the die, Abby? 6. And when you take 1 out of 6 plus 1 out of 6, you get? 4 1/3. Letter B says, what's the probability of rolling an odd number or a number less than 3? So think about this one. We want the probability of an odd number or a number less than 3. So Connor, how many numbers are odd? How many numbers are less than 3? 2. So the odd numbers are 1, 3, and 5. The numbers less than 3 are 1 and 2. Is there any overlapping? Julian? The 1. So this event has an overlapping piece. And the overlapping piece is the part that they have in common. They both have a 1 in common. So we are going to subtract that one value that they have in common. Because the number 1 is the piece that they share. So we've got the odd. We have numbers less than 3, which are just 1 and 2. But the 1 was counted twice. So we're subtracting that part. So if we look at those, we have 4, 6, or 2/3. Questions? So you kind of seeing the difference between the two. The third one underneath says a card is selected from a deck of 52. What is the probability that you get a 10 or a face card? There it goes. So find the probability of getting a 10 or the probability of selecting a face card. So your face cards are your jacks, your queens, and your kings. Odette, how many 10s are? 4. So we have 4 10s. How about face cards? 12. A 10 is not a face card, it's a 10. So the face cards are just your jack, your queen, and your king. So Odette, if we add those together, we get 16 52nds or 4 13s. Any questions with those 3? So that one was considered mutually exclusive. Part A was considered mutually exclusive. One event didn't overlap with the second. They didn't share a part that they had in common. Questions? So if you flip to the top of the next page, it says to use the formula to find the probability of A and B. And the formula that we're going to use is the probability of A or B, because this is the only formula we have, is equal to the probability of A plus the probability of B minus the probability of both. That's the only formula we have right now. So that's the only one we can use that contains the probability of A and B. So 200 students in senior class, 113 are either varsity athletes or on the honor roll. 74 seniors who are varsity athletes, 51 seniors are on the honor roll. It says find the probability that a randomly selected senior is both an athlete and on the honor roll. So there's a lot of information. See if you can read through it again. If you have a formula, formulas are plug and chug. So we just want to find the correct information to like replace the pieces of the formula. Our goal is to find the probability of both. That's that A and B part. That's the both part. So that would be the piece that we don't have something to plug in for. So try and like just read through it again. See if you can figure out what goes in for the A and B. What's the probability of A? What's the probability of B? So just starting with the probability of A or B, do they give us any information about it being one or the other? Maggie, do they give us any information about being one thing or the other?
Either varsity or
Yeah, how many students are either on varsity or honor roll? 113. So 113 students are either on the varsity or varsity athlete or they're on honor roll. So that probability would be 113 out of the 200. Maggie, what's the probability that they are just a varsity athlete?
74.
And the probability that they are just on honor roll?
51.
And our goal is to find the probability that they're both a varsity athlete and on honor roll instead of being one or the other. So if you add your two together, take it to the other side. Will, what is 74 and 51? Yeah, so we have 113. You're subtracting 125. That's going to give us a negative number, but we're also subtracting the probability of B and A, so it becomes a positive value. So will 125 minus 113 is? So the probability of A and B would be 12 out of 200. And then if we reduce that, maybe divisible by 4? Yeah. 3/50. Questions? So just plugging in the pieces, solving for the missing part. So if we knew one or the other, we knew them individually, but we wanted to figure out both. This number is going to be bigger because when you add the two together, there's already values that are counted twice. So there are 12 people that have both honor roll and the varsity athlete. So that's why that number is bigger. Questions? So the other thing that we're going to look at today is something called the complement of A. The complement is a little A with a hat on it. And it's actually finding the probability that the event is not in A. Or let's say the outcome. So the complement's kind of like the opposite. So you're finding the opposite of the probability of the A. And the way we find the complement is by taking 1 minus the probability of the event occurring. Because probability is supposed to be equal 100. So it's either in A or it's not in A. Together, they should be equal to 100% or 1. So that's why we've got that 1 there. So you take 1 minus the probability of A, then what's left would be the values that are not in A. So underneath there is a picture of 36 pairs of dice. These are rolling 2 dice and giving you all of the possible combinations. And notice that there is a difference between having a 2 and a 1 and a 1 and a 2. So it does matter which is rolled on one die versus the other die. So there could be 2 different options, which is why there are 36 outcomes. So we're going to see if we can try and use complements to help us figure out the values that we're kind of asking for here. So it says we want the fact that the sum is not 6. So by using complements, if we find the probability that it is 6, which is a lot easier to count because there's going to be less options, then we can take 1 minus that value, and then we have the complement. So where would the die pairs be equal to 6? So look at your options. Julie, where does that happen?
2 and 4, 4
So
and 2.
she said 2 and 4, and 4 and 2. That guy's right here. What other combinations would be equal to 6 besides 2 and 4, 4 and 2? Holly?
3 and
3 and 3. And also, Julian?
Five.
Julian. Say it again.
5
5
and 1.
and 1. Or 1 and 5. Notice that they're all on a diagonal. So the sum of 6 is on a diagonal based off of the way these dice are organized. So if I count the number that equals 6, we've got 1, 2, 3, 4, 5 out of 36. So that's the probability of rolling a pair of dice that have the sum of 6. By using complements, if I take 1 minus that 536, (31) out of the 36 remaining would not be equal to 6, which is everything else that's on here. But it's quicker to add up 5 things than it would be to count all of the remaining die. So that's why complements can be useful, because you're finding pretty much what's left by adding the shorter, the smaller value together. So if you look at the next one, it says the sum is less than or equal to 9. So it's probably easier to find the sum being greater than 9 because there are less options that add to be 9. So I'm trying to get you to think about complements. So look at all of the pairs of die. How many of them have a sum greater than 9? Because that's the opposite of less than or equal to 9. So looking at all of those options, if I start in the bottom right corner, we have 12, and then we have 11, and then we have the sum of 10. And then if I go to anything else, diagonally after that, I have 9. And we just want the values that are bigger than 9. So if I add those together, again we have 5. So this is 536. So by using complements, 1 minus 536 is again that 3136. So the probability that the sum is less than or equal to 9 can be found by using the complement. So say we go to the last one on this page. Find the probability that the sum is greater than or equal to 3. So again, think if it's greater than or equal to 3, it's probably easier to find the sum that is less than 3. You can always find the opposite, but you're just counting more. So I'm working on just finding the opposites of what the question is asking for. How many sums are less than 3? Julian? 3? So they could add to be?
1, 3, or 2.
So we want the sum being less than 3. So looking at the pair of dice, how many of them add to be less than 3? Just 1. So that top left corner, the sum of 1 plus 1 is 2. If I go to 1 and 2, that sum is 3. 2 and 1, that sum is 3. We're just looking for the sum being less than 3. There's just one of them out of 36, which means 35 out of 36 sums are greater than or equal to 3. So sum means add the two values together. So you're taking your pair of die and adding dice and adding them together.
Why don't you include the ones that are equal?
Because it says we want to find the probability that the sum is greater than or equal to 3. So the opposite of greater than or equal to would have to be less than if everything's smaller than that. Because if it's equal to it, it's allowed to be included in our actual probability that we're finding. Other questions? So I believe there are a handful of practice problems on the last page. So think about rolling a 6-sided number cube or die. Find the probability that the value that you're rolling is less than 4, so not greater than 4, just less than, or an even number. Number 2, you're going to use the formula. Plug in the pieces that you know to see if you can find the probability of both. Holly, how many numbers on a die are less than 4? 3, yeah. So you're not including 4 because it just says less than. How many numbers are even, Holly? 2? 3? So 1, 2, and 3 are less than 4. 2, 4, and 6 are even. And then we're subtracting the one time that the value is even and also less than 4. So you should have 5, 6. So those are considered events that are overlapping. They have something in common because they both share the number 2. 2 is even and it's also less than 4, so it has that both occurrence. Number 2, we have a survey of 125 people. 90 of them like orange juice or grape juice. 62 people who like orange juice, 43 people like grape juice. Find the probability that they like both. So our little formula is the probability of A or B can be found by taking the probability of A plus the probability of B minus the probability of that both occurrence. So just plugging the numbers in. 90 people like one juice or the other. 62 like orange juice, 43 like grape juice. We want to find the overlapping piece. So Abby, do you have a number of people that like both? Yeah, so 15 over 125. And if we divide that by 5, you get 3/25. Questions? So the last handful of problems, let's look at number 4, dealing with the cards. Number 3 goes back to the dice. You're picking one card from a standard deck. Find the probability of the following. Find the probability of choosing a red or a black card. So what would be the probability of choosing a red or a black card? Julian?
52 out of 52.
Yeah, so 26 of them are red, 26 of them are black. So we have 52 out of 52, or just one. 100% probability of getting a red or a black card. That's the only thing that exists in a deck of cards. They're either red or black cards. Part B says find the probability of choosing a face card or a red card. Emma, how many face cards are in a deck of cards? How many red cards are there? Are there any face cards that are also red? How many? Yeah, half of the face cards are going to be red, the other half are going to be black. That's the part that overlaps. So we take out that 6 cards that were counted as face cards and as red cards. So the overlapping part's the part you can't forget. You gotta subtract that part. So Emma, 12 plus 26 minus 6. 20? 20 what? 22? Which would be 11, 20.